Welcome back, class. In our last episode, or our last lecture, we were discussing the topic of what are known as two-step LEOVs. And it turns out that two-step LEOVs are simply a more complex or more complicated form of what are known as one-step LEOVs, or one-step linear equations of one variable. So we took a number of equations, such as something that looks like 1/3 x plus 4/5 is equal to 7/2. We took an equation such as the following, and we're able to solve for x, or solve for the unknown number, using a strategy where we apply first the additive inverse and then the multiplicative inverse in order to finesse this equation and get it into a form where x is on one side of the equal sign and all of your other terms are exactly on the other side of the equal sign. So how that kind of worked was we said, well, we leave the 1/3 x alone, but we examine whatever term happens to be added with the 1/3 x. And in this case, you have a positive 4/5 that is added to your 1/3 x. So you ask yourself, okay, what is the additive inverse of 4/5? And it turns out that the additive inverse of 4/5 happens to be negative 4/5. And so what we do then is we're going to add a negative 4/5 to both sides of our equation. 4/5 plus negative 4/5 by the additive inverse law becomes 0. And you've got 1/3 x plus 0 is equal to 7/2 plus negative 4/5. Okay, and then 1/3 x plus 0 is just 1/3 x. So you get 1/3 x is equal to 7/2 plus a negative 4/5. And there are a number of things we can do at this particular point in time. A lot of students are going to be tempted to try to deal with the multiplicative inverse law here, which is fine. Another option or another strategy would be to, of course, combine your fractions together, but you can't currently do that until you can find a common denominator. And so recall the strategy that I teach you guys in class is to multiply by the opposing base. You're going to take 7/2, you're going to multiply on the top and the bottom of 7/2 by 5/5. You'll take negative 4/5, and you're going to multiply this negative 4/5 by 2/2, or whatever the opposing fraction happens to be. The opposing denominator of the other fraction happens to be. All right. So now you just multiply. 7 times 5 gives you 35. 2 times 5 is 10. 5 times 2 is 10. Negative and positive is a negative. 4 times 2 is 8. All right. So you have 1/3 x. And you'll note I'm not really doing anything with the 1/3, right? I'm just, at this moment in time, just managing the fractions on the other side of my equal sign. So at this point, because you have like denominators, you can go ahead and add or subtract across your numerator, and you'll have 35 plus a negative 8. 35 plus negative 8 should be 27. So we'll have 27 over 10 is equal to 1/3 x. And depending on what the fraction happens to be, you may be able to simplify the fraction at that point in time. 27 is the same thing as 3 times 9. 3 does not divide 10, so there's really nothing we can do with the fraction. So at this point in time, what we'll do now is we are going to go ahead and use the multiplicative inverse. To do this, we consider what the multiplicative inverse of 1/3 happens to be. And what we discussed last time was that all you have to do to find the multiplicative inverse is flip your fraction over. So 1/3 becomes 3/1, and we would say 3/1 is the multiplicative inverse of 1/3. All right, but we can't just multiply this 1/3 by the left side of our equal sign. We have to multiply it by both sides of the equal sign. So I have to multiply 3/1 with 27/10 as well. as with 1/3. So now we do 3 times 1, which gives us 3. 1 times 3 is 3. You get 3 over 3x is equal to 1 times 10, which is 10. And you have 27 times 3. 3 times 7 is 21. Carry your 2. 3 times 2 is 6, plus 2 gives you 8. So you got now 81 over 10. And on the other side of your equal sign, 3 divided by 3 by the inverse law just gives you 1, which is what we expect, what we should expect at this point in time. And 1 times anything is just that something by the identity law. All right, and so this was our general strategy for solving two-step LEOVs. We first just start with an additive inverse. Note the first step here was an additive inverse. And then the second step was, once we kind of cleaned up the right side of our equation, we then focused on using a multiplicative inverse to get the x by itself. And it doesn't really matter how complicated or how complex the coefficients are in front of our x, or how complex the what are called constants are that are being added to x, or that x happens to be equal to. We're going to follow the same exact strategy. If I had decimals, I would follow the same exact strategy. If I have some funky looking expression, I'm going to follow the same exact strategy. And the reason for this is that, if we have something like 1/3 x plus 4 over 5 is equal to 7/2, and we start with a multiplicative inverse instead of an additive inverse, then what happens is, even though we know, okay, I need to multiply by 3 over 1, the truth of the matter is you can't just take 3 over 1 and multiply it with 1/3 x. Instead, what's happening is, according to the multiplicative property of equations, when you have some equation, so say this, we have some sort of expression, and I'll just call it equation with a little 1 down below. And that's just some complicated expression. And this equation, which could be rather nasty, is equal to something. When we use the multiplicative property of equations, and I multiply, say, both sides by some number, maybe I multiply by the number 2, I'm actually multiplying everything on the left side of the equation by whatever value I happen to be multiplying by. And whatever I do to one side, I also have to do it to the other side. Now, it may be that you only have one term on a specific side of the equal sign, such as is the case here with 7/2. But on the left side of the equal sign, you'll note that you've got 1/3 x plus 4/5. So if you were to do the multiplicative inverse first, you actually have to multiply by the entire quantity 1/3 x plus 4/5 on the left side of your equal sign. And then on the right side of your equal sign, you have to do the same thing. Now, the right side of the equal sign is not too much of a bother because you've got 3 times 7, which gives you 21. That's not too bad, right? But on the left side of the equal sign, you've got 3 times 1/3. You have to use distribution here. A lot of students are going to forget that they need to use distribution. So that's one thing that students struggle with, is just memorizing all of the different ways that you can manipulate a particular equation. So adding new ways to manipulate a particular expression isn't necessarily going to be helpful for students' understanding. And instead, my recommendation would be for students to just essentially use one methodology to approach equations and stick to it until they truly master that specific method. Now, in some instances, it's instructive to at least demonstrate to students that you can indeed start with a multiplicative inverse if you so choose, or if you so desired, but that we usually don't, because it'll lead to more steps. So what's going to happen here is you've got 21 over 2 on the right side of your equal sign, and you've got 1 times x, or just x, on the left side of the equal sign. 3 times 4 became 12. So now you've got 12 over 5 being added with x is equal to 21 over 2. And just like before, at this point in time, you can use the additive inverse to remove the 12 over 5. 12 over 5 plus a negative 12 over 5 by the additive inverse law that's guaranteed to be 0. You don't have to waste your brain cells. But you're now stuck in a position where you've got to add some fractions together that are kind of nasty. It's not to say you can't do it. You certainly can. But these are not necessarily the most ideal fractions to add together. So, but nevertheless, we'll give it a go. We'll give it a shot. So I'm going to use the multiply by opposing base method. And across your denominator, you've got 2 times 5, which gives you 10. 2 times 5, which gives you 10. You'll have 2 times 12, or 24, and 21 times 5. 5 and 1 is 5. 5 and 2 is 100. So I got 105. Okay. Now note what's going to happen. You've got 105 minus 24 all over 10. Go to the side of your page. You're going to take 105. You'll subtract 24 from it. Go ahead and borrow a 10. 10 minus 2 gives you 8, right? 5 minus 4 gives you 1. So we are indeed going to obtain the same answer we had before, which was 81 over 10. All right. So for today's lesson, we're going to discuss the topic of what happens when you start to encounter equations that are very, very complicated, what we call multi-step LEOVs. Well, the good news is, for us, we have a problem-solving strategy that will allow us to address any instance where we might be presented with a more complex linear equation of one variable. And that is, you're going to start with whatever equation you happen to be given. So if you're given a multi-step LEOV, you got to start with that multi-step LEOV. And it's going to look complicated. It's going to be more complicated than what we've been dealing with. Nevertheless, we're going to use the rules of algebra one step at a time. And what we can do, or what we can always do, is we can finesse the multi-step LEOV to become a two-step LEOV, which is really, really fascinating. And then once we get a two-step LEOV, we can use the rules of algebra again, but specifically we'll use the additive and then multiplicative inverses to finesse the two-step LEOV in the method we've described previously to be a one-step LEOV. And from there, you're able to obtain your solution fairly easy enough. All right, and as long as we work very cautiously one step at a time, the pattern for solving all multi-step LEOVs is as follows. Like, you'll always be presented with this equation. There are going to be a number of different cases for multi-step LEOVs. You'll take, depending on the case, we're going to take a number of rules of algebra that are rather predictable. Eventually, we'll be able to finesse the equation into what is known as a two-step, from a two-step, a one-step, and then finally, we'll be able to arrive at our solution. Now, the good news is there are only a number of specific cases that you encounter with multi-step LEOVs. The first and easiest of which is what is called a collecting like terms problem statement. And what this kind of looks like, although there are a variety, there are presumably thousands of different ways you might encounter a multi-step LEOV where you have to employ collecting like terms. But how this might look is you may be presented with something like 2x plus 5 plus 10x minus 4 is equal to 35. Okay, this would be a very classic case where you're collecting your like terms together, and we'll talk about what that means. Another situation where you might use the rules of collecting like terms would be whenever you have a situation like, say, you've got 10x plus 7 is equal to 14 plus or minus 3x. So when you've got x terms, but the x terms themselves are on both sides of your equal sign. Okay, that would be an example of collecting like terms. The second type of equation that you could encounter when it comes to, or not equation, but the second category of multi-step LEOV, rather, would be what is known as a distribution law style problem statement. So for a distribution law style problem statement, you're going to be faced with a equation where, as the name implies, you're going to need to use the distribution law in order to solve the equation. In the most simplest forms, you'll have some number which is multiplied by a sequence of terms that are either added or subtracted from each other, and that is equal to something else. So that is the most simplest form of a distribution law style problem. In a more complex case, you may have something like, -2 times the quantity x minus 7 plus 3 times the quantity x plus 4 is equal to 14. Or, of course, you might have a combination of different things going on. So you might have, say, 4 times x minus 2 is equal to -10 plus 2 times x plus 5. Something like this. So you could have a sequence of different places where you need to employ what is known as the distribution law. We'll show you how to do that here in a second. Okay, so the final instance, or the final category, rather, of a multi-step LEOV is what we call a combination style multi-step LEOV. And what this looks like is it's going to be something that's, at least on the surface, pretty nasty. You might have something like, 7 times the quantity p plus 2 over 2 plus or minus, maybe -4 times p minus 6 all over 3 is equal to 10. So some expression where there not only is a bunch of distribution rules that you have to follow or you have to account for, but also there are generally going to be some fractions that you need to take notice of or account for. And so in these style problem statements, you're going to have some more steps naturally, and or some interesting techniques that you can employ in order to simplify everything. All right, but without further ado, let's just look at how we deal with the collecting like terms problems, which are going to be the most basic multi-step LEOVs that you encounter. First of all, what does it mean when we have what is known as like terms? So I'm going to introduce a definition for like terms. When we have a situation where you're dealing with like terms in mathematics, this might look like something such as 5 times the quantity x plus 3 times the quantity x. And the question will ask you, what is this quantity equal to? Now, if we use 5 times the quantity x plus 3 times the quantity x and ask ourselves, what is this equal to? The way that I phrase that particular mathematical statement, even though it's correct, doesn't necessarily lend us to the intuitive approach that we need to take in order to obtain an answer. Instead of saying 5 times a number, I could say 5 sets of some quantity added with 3 sets of some other quantity. And the reason why I would want to frame this particular expression using this statement, where I use 5 sets of blank added with 3 sets of blank, is because we can start playing the game of filling in the blanks. What if I use the word apple in this blank here? And of course, I use the word apple for this blank here. Whatever word I chose, if I choose apples, I could talk about apples. If I choose bananas, sets of bananas, I could talk about sets of bananas. If I talk about sets of pears, I talk about sets of pears. So, but regardless of the specific fruit or the specific item that I choose to represent my sets of something, once I start talking about 5 sets of apples added with 3 sets of apples, and I ask the question, well, how many sets of apples do I have left in total? Got 5 sets of apples added with 3 sets of apples. Well, I clearly should have 8 sets of apples. At least reason would dictate that I should have 8 sets of apples. That's an argument that I could make for why 5x plus 3x should equal 8x. Another argument that one could make would be to start giving yourself a value for x. We could ask ourselves what happens if we let x be, say, the value 1. So if you have this expression, 5x plus 3x, and we ask ourselves, what is this equal to? In order to help determine what's going on with this 5x plus 3x, we could start defining what x has to be and then see if there might emerge a pattern there in the numbers. So if I let x be 1, if I just say, okay, I don't know what x is, but suppose x was 1. Suppose it's 1. What happens? Well, we have 5 times 1, which gives me 5, added with 3 times 1, which is 3. 5 plus 3 gives me 8. If we let x equal to 2, you've got 5 times 2 plus 3 times 2. Well, you've got 5 times 2 is 10, 3 times 2 is 6. It's 10 and 10 plus 6 is 16. And if you let x be 3, you'd have 5 times 3 plus 3 times 3. So that would give you 15 plus 9. And 15 plus 9 should give me, let's see, 24, correct? Okay, and then now you're going to ask the question, okay, I've got this sequence of numbers, 8, 16, and 24. How can I relate these sequence of numbers together? Students who are familiar with their multiplication tables should be aware that 8 times 1 gives them 8. 8 times 2 gives them 16, and 8 times 3 gives them 24. So really what I'm doing when I'm taking this expression and I'm plugging in 1 for x, this is the same thing as if I had taken 8 and I multiplied it by 1. It would give me the same answer. And if I took this 5 times 2 plus 3 times 2, that's the same thing as if I had taken 8 and multiplied it by 2. If I took 5 times 3 plus 3 times 3, that's the same thing as if I had just taken 8 and multiplied it by the quantity 3. And I hope that everybody can see that. And it actually doesn't matter what value that I multiply, what value I set for x. Whatever value it happens to be, all I'm going to do in order to get an easier answer is take 8 and multiply it by that value for this particular expression. Okay, so I hope I've made a good case algorithmically for why 5x plus 3x should equal 8x. But algebraically, what's going on here? Why is it that 5x plus 3x is equal to 8x? Is there perhaps an algebraic rule that we can use in order to determine that indeed we will get 5x plus 3x, and that has to equal, without a shadow of doubt, 8x? And the answer is yes, there is in fact an algebraic rule that we can use, and it is the distribution law. At the beginning of the semester, we very briefly covered the distribution law. We said that whenever you have a number that's multiplied out in front of a set of parentheses with a bunch of terms added together, this is the same thing as taking your term out in front and multiplying it with the first number in the set of parentheses and adding it with the number that's out in front multiplied by the second number in the parentheses. Now, the reason this works from a math perspective is that suppose you have a case such as 5 times 10. Well, 5 times 10, I hope everyone would agree, is equal to 50. And all we really do when we're talking about the distribution law is we're saying, look, what if I took this number, 10 in this instance, and I replaced it with something that added to be 10? How might I take the number 5 and multiply it across this sequence of terms in order that I still arrive at 50, which I have to arrive at, because according to PEMDAS says that if you had an expression 5 times 7 plus 3, you need to attack the inside of the parentheses, i.e., you need to add 7 and 3 together, giving you 10, and then multiply. Okay, correct? So by PEMDAS, we've not changed anything here. We know the answer to 5 times the quantity 7 plus 3 has to equal 50. And the answer is that you basically take your number, and as long as you multiply it across the sequence of terms that are being added together, you will in fact get 50. So 5 times 7, of course, gives you 35. 5 times 3 is 15. And it turns out that 15 plus 35 will indeed be 50, because 5 plus 5 is 10. 10 and 10 is 20. 20 and 30 gives you 50. Okay, so that is the justification for the distribution law. But recall that there are actually two different forms of the distribution law. There is the left-handed distribution law, which is what is written here. It's top row. And then there's also the right-handed distribution law, which is what is written below, where you have a quantity multiplied with some value. And in either case, it turns out that right-handed and left-handed distribution are actually equal to each other. And so what happens in the instance of adding like terms is that adding like terms can be thought of as distribution in reverse. When you have this 5x plus 3x, you'll note that the x is the same value. And if you line your 5x plus 3x up with your distribution law, you'll see that it's the same as the value a in your distribution law. So if you were to allow the 5 to be your b and the 3 to be your c, then by the distribution law, you should be able to do some rearrangement here. You would have 5 plus 3 on the inside of a sequence of parentheses, which of course gives you 8, and you would have 8 multiplied by your x. Okay, so adding like terms works as a consequence of the distribution law. That is the long and the short of it. So when you have an adding like terms problem, let's just give an example. Suppose you have a problem statement 5x plus 3x plus 10 is equal to 20. And the question asks you to solve for x, or solve for your unknown. What you're going to do is you're going to say to yourself, okay, I've got 5 apples plus 3 apples. That gives me 8 apples. And if you do this, voila, you now have a two-step LEOV. I think one node just crashed, so let me open that up. So we have a two-step LEOV. At this point in time, you can take 8x, and what we'll do is we'll add a negative 10x to both sides. We're using our additive inverse law. 10 plus a negative 10 gives you a 0. And you'll have just 8x plus 0 is equal to 20 minus 10, or 20 plus a negative 10, which should give you 10. 8x plus 0 is just 8x. So we'll have 8x is equal to 10, and you can use your multiplicative inverse. Don't be afraid of the word multiplicative. Say it 20 times to yourself so that you're not scared of it. All of these words are Latinate, okay? So part of the challenge of mathematics is you have so many different Latinate terms. Because we don't speak Latin, that can often lead to a lot of confusion for students. But if we just repeat the word over to ourselves, this tablet's so frustrating because it's getting hot, I think. So it's not wanting me to write because the cursor is jumping whenever I write. So usually means the laptop's getting hot. But yes, if we just repeat these words to ourselves over and over and over again, they'll become less intimidating, and that will lead to a greater understanding on our part. At least we won't be shutting down every single time we begin the process of going through one of these math problems. You guys all have the ability to do this, okay? Every single one of you has the ability of doing this. All right, so let's do another example. In many instances for collecting like terms problems, you're going to have terms that are on both sides of your sequence of parentheses. You may have something like 7t plus 15 is equal to 35 plus 8t. And of course, the confusion that arises for students is, do I need to move terms from the left side of my equal sign to the right side, or do I need to move my terms from the right side to my left side? And the answer is whichever one makes you happy. Because ultimately, it's not going to matter if you move your terms from the right side to the left side or vice versa. Really, what we're looking for is we're looking to finesse this equation if we're solving for an unknown number. We're going to get t is equal to blah, 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 or we'll have blah, blah, blah is equal to t. It really doesn't matter if I say t is equal to something, or if I say something is equal to t. In either instance, we have what we're looking for. We know what t happens to be. And so we would say that we've solved the equation. From personal experience, what I would tell students is, to make your life easier, you really want to pick up on which term happens to be greater than the other terms. So you'll see that you've got a coefficient of 8. And what that generally indicates to me is that I'm going to want to move the variable 7t from the left side of my equal sign to the right side of my equal sign. So let me go ahead and do that. I'm going to add a negative 7t to both sides of my equal sign. And note that I'll use my additive inverse on the right. So I'm adding it to the right of 7t. And that gives me 0t plus 15, because 7t plus a negative 7t, that's going to be 0t, or simply 0. And on the left side of my equal sign, I've got 8t plus a negative 7. So this is going to be 8t minus 7t because a positive and negative is a negative. So you've got 8t minus 7t. Now you'll note that 0 plus 15 is just going to be 15. And when we talk about 35 plus 8t minus 7t, well, that would just be 1t. 1 times t, of course, is just t. Now you have a two-step LEOV once again. So now we can go ahead and we'll use the additive inverse of negative 35 since I got positive 35 parked next to my t, and I want my t by itself. So I'll go ahead and I'll add a negative 35 to both sides of my equal sign. On the left side, I'm sorry, on the right side of the equal sign, 35 plus a negative 35, that's going to be 0. So now you just have 0 plus t. On the left side of your equal sign, you've got 15 positive negatives and negatives, so 15 minus 35. Note that when we're subtracting numbers and we're trying to determine if something is a positive or a negative number, you just look for which value happens to be of greater magnitude. So you'd say, I've got $35 in debt, but I pay you back $15. I would still owe you a debt outstanding. Okay, I would still owe you money after paying you back $15. I don't clear my debt with you if I owe you $35 in the first place by only paying you back 15. I have to pay you more than what I owe you naturally for me to clear my debt, or at least the amount that I borrowed in the first place. So when we've got 15 plus negative 35 and we say that's 15 minus 35, what we're going to do is we go to the side of our page and we actually take the difference of the two numbers as though we were doing a subtraction problem. So you're always going to set up like it's an ordinary subtraction problem. In this instance, you do 35 minus 15. 5 minus 5 is 0. 3 minus 1 is 2. So you get the answer is 20. But in this instance, you know that you have a greater amount of money outstanding. So it's going to be a negative 20. All right. 0 plus t is just t. So you've got t is equal to negative 20. And that's our answer. All right. Now let's look at some of the distribution law style problems. So for the distribution law style problems, you may have it set up 5 times the quantity z plus 4 is equal to 25. And the question, of course, is solve for the unknown variable. Solve for the unknown number, solve for the unknown quantity. What we're going to do for a distribution law style problem is we're going to use the distribution law. You can take the 5 that is out in front of the sequence of parentheses, and remembering the distribution law, you may multiply the 5 by each one of the terms inside of the sequence of parentheses. So you're going to take 5, you multiply it by z, that gives you 5z. But you take 5 and multiply it by 4, and that gives you 20. So you've got 5z plus 20 is equal to 25. Now what we have to do is we need to add a negative 20 to both sides of our equal sign. So 20 plus a negative 20, that gives you 0. So you've got 5z plus 0 is equal to 25 plus a negative 20. Well, 25 plus a negative 20, and that's just going to be a 5. Yeah, 5z plus 0 is just 5z is equal to 5. And at this point in time, you can multiply 1/5 on both sides of your equal sign. 5 times 1/5 is just 5 over 5, which gives you 1. So you get z is equal to 1. And that's your answer. All right, let's look at a more challenging distribution law problem statement. Suppose you have something like the following. 5 times the quantity z minus 4 plus 10 is equal to 2 times z plus 2. And the question, of course, asks you to solve for the unknown number. How you approach the vast majority of these distribution law problems is you're just going to start by using the distribution law. So you'll do 5 times z plus, now here's the critical part. You want to be careful when you've got some quantity minus something else inside of a sequence of parentheses. Go ahead and write that quantity as a negative number. So instead of z minus 4, go ahead and write it as a negative 4. You're going to distribute your 2 to your z, and you'll have 2 times 2. Positive, negative is a negative. 5 times 4 gives you 20. And you'll just have 5 times z. Negative 20 plus 10 gives you negative 10. So if I owe you $20, but I pay you back $10, I must owe you $10. 2 times 2 gives you 4. So we have 2z plus 4 is equal to 5z minus 10. Now we have a collecting like terms problem. In many instances, the distribution style problems will simplify to being a collecting like terms problem statement. So once you do the distribution law and you simplify, you'll be left with a collecting like terms problem. And so following the procedures for a collecting like terms problem, you'll see that I've got a 5z here. So, and 5 is bigger than 2. So what I'll do is I'm actually going to move my 2z from the right side of my equal sign to the left side of my equal sign. So I'm going to add a negative 2z to both sides of my equal sign. 2z plus a negative 2z, that just gives me 0. So I've got 0z plus 4. That's going to equal 5z plus a negative 2. That's going to be 3z minus 10 is equal to 0z plus 4. So that's 0z is just 0. So we have 0 plus 4 on the right-hand side. And now we're almost there. We've got a two-step LEOV. Okay. Now with the two-step LEOV, you're almost finished. Go ahead and use the additive inverse on both sides of your equal sign. You're going to get negative 10 plus 10. That gives you 0. So you have 3z plus 0 is equal to 4 plus 10, or 14. Now you have a one-step LEOV. So we just need to use their multiplicative inverse. Multiply by 1/3 on both sides of our equal sign. 3 divides out with 1/3, and that just gives you 1. 14 times 1 is 14, and 14 is not divisible by 3, so your answer is z is equal to 14/3. One thing that students should note for these problem statements is that we're usually not going to go out of our way to write down a decimal answer or a decimal approximation once we get finished solving the problem statement. Okay, like if you get z is equal to 14/3, I don't actually care if you go to the side of your page and do the division. In fact, it's a nicer answer if you just leave the problem statement as z is equal to 14/3. Where this is not the case would be you're perhaps an engineer, maybe you're a machinist, and you're solving for a problem involving, say, something for construction applications. Okay. Generally, for construction applications, the measuring device that you're going to use is not necessarily marked in fractional terms. Now, of course, for the United States system, we usually have our measurements in terms of fractions. So like half a foot, quarter of a foot, third of a foot, et cetera, et cetera. But on the other hand, what's really going to happen in construction applications is you're usually going to be measuring using decimals. And so in that instance, it would probably be best if you went ahead and simplified this expression, not simplified, but if you rather converted your fraction to a decimal at this point in time. But for everyone else, if what we're doing is we're just, solving some random calculus question, if all we're doing is solving an SAT style question, unless the specific problem statement asks us to solve the equation and then convert to a decimal or find a decimal approximation, then and only then are we going to worry about a decimal. Okay? So unless explicitly stated, you are done when you get z is equal to 14/3. All right, let's look at one combination style problem before we call it a day. So for combination style problems, you're usually going to be given this nasty nonsense where you've got a bunch of fractions. And there are two different ways of resolving these nasty looking problems where you've got a bunch of fractions. One of which is to clean this up a bit, if it's possible to do so, and essentially rewrite this expression or rewrite the equation in such a way to where this is just a distribution law problem. However, while that's possible for this particular instance, it's not always possible for every single instance where you've got some sort of equation where terms are either in your numerator or they're in the denominator potentially. In some instances, you have variables that are in both the numerator and the denominator. And then the question is, what's the general principle for being able to manipulate these these more complicated multi-step LEOVs? And the answer to that question is, what we're going to do is we're going to incorporate a new technique called the Hindu-Arabic technique. Now, the reason I call this the Hindu-Arab technique is that this technique is described in very, very ancient scrolls, the earliest of which were written down by both the Hindu and the Arab mathematicians. And it was very popular, and it is very popular, rather, even to this very day in India, that when you're presented with one of these problem statements where you've got a bunch of fractions, to use this particular technique in order to clean up the problem so that you don't actually have an equation with any fractions at all. And so how this works is you're going to look to the denominators of your fraction, and you actually have to calculate what's known as the LCM. Now, earlier in the semester, we talked about how to calculate the LCM. We know that if you have two numbers that are prime, the LCM of those two numbers is just, you take both numbers and you multiply them together. So in this instance, I'm going to find the LCM of 2 and 3, which are the denominators of these fractions, and the quantity that you have to work with is 6. And so the idea is, if I take this 6, I'm going to do something very special to this entire equation. I'm going to multiply across the entire equation by 6. When I do this, I'm going to magically be able to clean up this expression to where I don't have any fractions at all. So how does that work? Well, when you multiply this 6 across the left side of your equal sign, the 6 has to be multiplied with 7/2 and p plus 2. And then the 6 will be multiplied by -4/3 p minus 6. And we need to not forget that 6 has to multiply with 10. So at this point in time, 6 will divide out with 2. 6 divided by 2 gives you 3. So this will be 3 times 7 times the quantity p plus 2. And over here, we've got 6 will divide out with 3, leaving 2, and 2 times -4 is what we're left with. On the right-hand side of our equal sign, 6 times 10 is just 60. But you'll note that 3 times 7 is 21. So we have magically reworked the entire equation where now we don't have any fractions. Okay. At this point in time, go ahead and use your distribution law. You're going to have 21 times P and 21 times 2 plus a -8 times P plus a -8 times -6. 21 times P is just 21P. 21 times 2 is going to give you 42. Positive and negative is a negative, so we have a -8P. And negative and negative is a positive. Positive and positive is a positive. 8 times 6 gives us 48. Now we can go ahead and use the commutative law at this point in time. You're going to want to park your 8 next to your 21P and your 42 next to the 48. That's the commutative law. Remember, the commutative law says you could take any 3 or more numbers, actually 2 or more numbers, and I can add these numbers in any order. So 1 plus 2 plus 3, that's the same thing as 3 plus 2 plus 1. Even though 21P doesn't look like a number, it really is just some value. Because if we knew what P was, you would take 21 and multiply it by P. P was 1, you'd have 21 times 1, or just 21, right? So it makes sense that I can bring forward the -8P, park it next to my 21P, and at that point in time, we would have an adding like term situation. So 21 minus 8, that gives us, let's see. 13. And we need to add 42 plus 48. So let's go to the side of our page. 42 plus 48. 2 plus 8 gives you 10. Carry the 1. 1 and 4 is 5. 5 and 4 gives you 9. So you've got 13P plus 90 is equal to 60. Of course, we can go ahead and use your additive inverse. Add a -90 to both sides of your equal sign. 90 plus a -90, that gives you 0. So you have 13P plus 0 is equal to 60 plus a -90 is the same thing as 60 minus 90. And of course, 60 minus 90 gives you -30. 13P plus 0 is 13P. And now you have a one-step LEOV. Go ahead and use your multiplicative inverse, multiply by 1 over 13, the number, and flip it. What you do to one side, you have to do to the other side. So multiply by 1 over 13 with -30 as well. 1 over 13 times 13, that's going to be 1 by the inverse law. So you just have 1 times P is equal to -30 times 1 is -30. So you have -30 over 13, and 1 times P is just P. So you have P is equal to -30 over 13. And that's your answer. Note that the Hindu-Arab technique works for not just instances where you have, say, a multi-step LEOV, such as the following, but actually any instance where there are fractions inside of a specific linear equation or even nonlinear equation. So for example, if you had, say, 4/3 x plus 2 over 7 is equal to 5 over, I don't know. Let's do 5 over 3, just to make this problem a bit more simple, a bit more simplified. Do 5/3. If we wanted to clean up this equation, even though it's a two-step LEOV, and we could go through the process of using our additive inverse and then our multiplicative inverse, if we wanted to clean up this equation so that we're left with a two-step LEOV that doesn't have any fractions, what you would do is you would look to the denominators of your fraction, and you want to calculate the LCD, not the LEV, but LCD of 3 and 7. Note that 3, 3, and 7 is the same thing as just calculating the LCD of 3 and 7, or LCM, least common multiple. So the least common multiple between 3 and 7, because those numbers are both prime, you just take 3 times 7 and you get 21. So what happens here is if you take the number 21 and you were to multiply it across this entire expression, as long as you do this very carefully, you'll have 21 times the quantity 4/3 x plus 21 times the quantity 2/7 is equal to 21 times the quantity 5/3. Now, what's going to happen here is the 21 will divide out with the 3. 21 divided by 3 gives you 7. It's not that the 21 disappears, it's that it divides out with the number in the denominator. So you'll have 7 times 4 times x plus, here 21 divides out with 7. 21 divided by 7 gives you 3, so you'll have 3 times 2. And here 21 divides out with 3. 21 divided by 3 gives you 7, so you'll have 7 times 5. So now you're left with 7 times 4 or 28x plus 3 times 2 is 6 is equal to 7 times 5 is 35. And so you've got a two-step LEOV where the x value, if you were to solve for x for this specific equation, assuming that you did your math correctly, meaning you found the correct LCM and you did your multiplication across the entire equation correctly, okay, that's an assumption. So you have to actually practice with this technique to get good at it. But assuming that you pulled it off correctly, you will be left with an equation where you've got a two-step LEOV now, but you don't have any fractions. So it's much easier for you to deal with this problem statement. So you've got 28x is equal to 29. And of course, you can now use the multiplicative inverse of 28 on both sides of your equal sign in order to get your x by itself, which in this instance, you'd find that x is equal to exactly 29 over 28. Assuming that we didn't make any mistakes, this should be our answer. Now, students might ask, why would I care to do that, though? Why would I care to find this shortcut of being able to rewrite an equation without a bunch of fractions? Other than the fact that not dealing with fractions is, in many instances, a lot simpler for me conceptually, meaning I don't have to remember all of the fraction addition or subtraction rules, things like finding a common denominator, blah, 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 blah. And the answer is usually, generally for these types of questions, going to be that there are instances where it's not exactly easy for us to actually, find common denominators at all. So for example, if you had a two-step LEOV where you had 357 over 284, t plus 682 over 1045 is equal to 1082. Imagine trying to solve this problem by hand, which is what the ancient people were stuck with, right? Like in 700 AD, when the Arabs were first inventing algebra, there weren't any calculators. There was an abacus. The Arabs had invented a tool for counting called the abacus by that point in time. So they did have this newfangled counting device, or relatively new device that would allow them to perform calculations much more easily and much more efficiently than what they were used to doing prior to the invention of the abacus. That's true, but they're still stuck with having to do all of this equation balancing, presumably. And for the Romans to even begin to approach an equation like this would have been just madness. They probably wouldn't have done it. They would have just used some sort of estimation technique in order to get an approximate answer for these types of problems. So there would have been no way to even get an exact solution at all. So what the Hindus and the Arabs would do is they would say, okay, well, I'll calculate the LCM of 284 and 1045. Now, of course, that's not exactly the easy thing to do for us, especially. It's not exactly easy for us to consider, performing this LCM technique, but it's doable. It's certainly doable. Okay. For the sake of time, I would probably go to a website called Wolfram Alpha, and I would ask them to help me calculate the LCM for this problem statement. I'll ask them to help me calculate the LCM of 284 and 1045. And when we hit enter, the answer to this problem statement is that the LCM of 284 and 1045 is going to be 296,780. So you're going to take 297, what was it? 296,780. 296,780. And what this LCM is telling me to do is it's saying you need to multiply this quantity across this entire monstrosity. So 357 over 284 t plus 682 over 1045 is equal to 1082. And when you do this isn't to say this is going to be an easy task, mind you. But what's going to happen is you'll have this 296,780 that will be parked out in front of 357 over 284. And the 284 is guaranteed to divide this 296,780. That's guaranteed to happen. So 284 will divide 296,780. And the same thing will happen here for 296,780 times 682 over 1045. Your 1045 will divide this quantity, and then you'll just be left with performing a bunch of multiplication operations. And even though that's still kind of a mess, right? It's not exactly as difficult as, balancing a bunch of fractions in addition to all of this nonsense. So 296,780 divided by 284, for example, gives us exactly 1045. So we have 1045 times 357 here. And then when we do 296,780 divided by 1045, we should be left with exactly 284. But go ahead and do that calculation. And 45. Yeah, so we're left with exactly 284. So we'll have 284. And I'm sorry, my t got lost. So I'll need our t back. Times 682. And this will be equal to 296,780 times 1082. And all of that stuff will be equal to each other. Again, this isn't exactly going to be an easy problem because really the challenge here is that you're going to have a bunch of pretty arduous multiplication by hand problems themselves, and then you're going to have a fairly arduous, presumably, subtraction problem. But it is doable. It's totally doable. You can do this, and the ancient mathematicians had to do these types of problems all the time. So I hope that everyone can see the utility of being able to find the LCM of two or more fractions if you are presented with one of these multi-step linear equations of one variable problem statements, and then multiply by whatever that LCM happens to be. In this instance, it appears that the LCM of 284 and 1045 was 284 times 1045, or 296780. So that's that's a little bit upsetting. Usually when you have really, really big numbers, you'll actually find a least common multiple that will be smaller than the product of the two numbers themselves, for sufficiently large numbers, that is, assuming those numbers are not, I guess you would call it co-prime, meaning that they don't have terms that don't divide one another. Okay, that's all I've got for you guys. Take care.